Okay, hello everybody. Welcome to the ninth Ivy paper reading group session. We're really excited this week to have Dr. Ronald Clark with us. So Ronald is an associate professor in the Department of Computer Science at the University of Oxford. His research lies in the intersection of 3D computer vision and computer graphics, with particular focus on building algorithmic frameworks to capture 3D representations of the world in real time. We're really excited to have Ronnie joining us today, where he'll be going through some of his research. And obviously for everybody listening in on YouTube, feel free to ask questions as we go through. We'll be doing the same in the room here as well. But without further ado, welcome, Ronnie. Stage is yours.
Okay, great. Thanks, Dan. So just to check first, the audio is working and everything. Everyone can hear me?
Yeah, it's working.
Okay, perfect. Yeah. So I guess the presentation today will be a bit different from like the standard reading group, because I thought it would be good to just kind of give some overview of like the research that we've been doing in my group, and generally this concept of like perception and reality capture, as you'll see in the presentation. So this specific presentation, it'll focus on one part of this, as you'll see in a bit, but basically how do we do machine perception for estimating motion and geometry, so capturing maps and the geometry of scenes. Okay, so before we get started with that, I think it's good to kind of take a step back and just have a kind of broader overview of what we're trying to accomplish with this. So say you're standing in a room looking at the environment around you. So basically, when you look at the scene around you, you use your eyes to see what's in the room. You identify objects, make a spatial kind of like representation of what is in the world around you. And this representation that you make in your mind is what you then use to kind of interact and explore, the world. So now when we bring in kind of robots, mobile devices, computers, ideally we want them to be able to kind of simultaneously interact with the same space or the same area that we are in. So the only way to accomplish this is if we can sort of imbue these mobile devices or these robots with the same understanding of the world as we have. So basically, this mobile device or this robot should have a shared world model with whatever we are perceiving, in the space around us. So this kind of like shared representation of the world is exactly what my research is trying to accomplish, and we kind of like call this process reality capture or machine perception. So an example of where this kind of reality capture or machine perception is very useful. I mean, this is just a simple example. I'm sure you can think of many, but say you're looking for your keys, you don't know where you've placed them, and you want to ask, your Siri or your assistant robot where your keys are. So in order for the mobile device or the robot to actually answer this question properly, you would need this shared world model where the robot has localized and actually placed, objects and items in the space where it is physically. So without this shared world model, you can't actually do even simple tasks like this. Okay, so there's a number of kind of characteristics or like properties of the world that we want to capture with this in this process. And the first of these is motion. So this is actually the one that I'll be looking at today. So say you have a mobile robot trying to kind of navigate around a kitchen to clean the floor, or like pick up the dishes or something like that. It needs to understand where it is in order to actually get to the target location or get to the object that it wants to interact with or manipulate. So this process of like estimating the location of the device, or estimating the location of it, is kind of like a fundamental problem in both robotics and computer vision that ties into this concept of digitizing the world, or understanding where you are with respect to the real world. So the other two properties that my research looks at is kind of understanding the light and also the geometry, which I haven't gone into much detail now, because the papers that I'm going to be looking at are focused mainly on this concept of motion estimation and somewhat mapping the space as well. So the applications of this, as I've mentioned, there's a wide range of applications where you want this type of capability. It's not limited to a specific area. So the particular applications that I kind of am interested in is augmented reality, so AR, VR, headsets and devices. They need to know exactly where the device is, so that you can add virtual objects into the world, so that you can kind of augment it with the 3D or the digital scenes that you want. The second one is autonomous machines, robots, things like that. So as I've mentioned, they really need to understand where they are in order to be able to interact with the stuff around them. And then the third one is natural sciences. So in many cases, so medicine, if you have an endoscope or something like that, you kind of also want to know where that sensor is, how it's moving with respect to, for example, the body, or if you flying drones around, for example, to do autonomous inspection of trees and forestry or agriculture, you also need to know this information. So the thing is that in the real world, it's not as easy as kind of just saying, okay, let me estimate the motion of my device, or find its location by looking at distinctive features and stuff in the images. And the reason for this is because the real world is not that ideal for kind of computational, for in an algorithmic sense. And that's because there's so many distractors, there's so many moving objects. So in this case, you can see there's people moving around in the scene at the bottom. You don't really have stable features. There's changes in the scene itself. So kind of the time of day changes, there's weather changing, there's shadows, occlusions, all these things. So these factors kind of make it really difficult to estimate anything from the real world, especially kind of in a robust way. Because if you can't deal with all these kind of nuisance factors, your estimates, obviously get inaccurate, your localization fails, your robot doesn't know where it is, it doesn't know what it's looking at. So all these challenges are exactly the ones that we need to address to get a robust perception system. So just taking a look at how I've actually addressed these, or how my research kind of tries to address these problems. I kind of categorize it into three different things that you can work on to actually try and improve these perception models. So the first one is the memory. So I think in many or most of the current algorithms, and especially traditional ones, there wasn't really a sense of the machine or the vision algorithm having a concept of memory. So they weren't able to remember what they estimate in the past, or what their previous kind of perception of the world was, and then use that to make inferences about the future ones. And the reason why this is very important is, for example, say you're driving, or say you have a autonomous vehicle that's driving along a road. If it sees, for example, the same McDonald's or the same road sign, and uses that as a landmark for localization, and thinks, oh, it's 50 kilometers or 10 kilometers back from where it actually is, that's obviously a major failure for your autonomous system. But if it can remember that, oh, I've already passed this specific this McDonald's, and this is a new one, or I've traversed at least 10 kilometers, it can then use that to make a more robust estimate of the current location. So I'll get to that in a bit, but that's just one example of like where memory can kind of help. Then the second way in which we can address, these challenges is by working on better representations. So in order to represent the world in a digital manner, especially kind of a 3D world that's changing over time, we need a very good representation to do that. So traditionally, these representations have been kind of point clouds or voxel grids, and things like that. But all the kind of traditional representations have some limitation, whether it's like in terms of the memory efficiency, whether it's in terms of the robustness, or what they can represent. So working on better representations of the world is also one way in which we can get, better, more robust algorithms for machine perception. And then the final kind of aspect that we can tackle is inference. So if we have a representation of the world and we have a way to kind of store past estimates and store, what the machine has been doing in the past, then we need a way to do inference or like predict what is going to happen in the future or what the current state of the world is from the sensor data that we're observing. And this inference part of it is usually solved by optimization methods, filtering methods, things like that. But again, although there's a lot of fundamentals and a lot of work in this area from many years ago, those traditional algorithms are usually kind of fragile, and adapting them to like a more robust and real world working kind of solution needs a lot of engineering, a lot of kind of like thought and design to actually get to that. So given that is kind of like the backdrop of the problem that we're trying to solve. In this presentation, I'm going to look at basically 4 different works or 4 different papers, just at a high level. So not really going into the sort of specifics and the technical details and so forth. But the 4 that we're going to look at are all related to this problem of motion estimation and mapping. So estimating the geometry of like the scene or the geometry of the objects around you. So the first 2, DeepV0 and VINet, those are only for odometry, so motion estimation. And then the last 2 are bringing into this a joint estimation of both the motion of the robot or the device and doing some mapping at the same time. So we'll get to like how these work in a bit. Okay,
Can I ask one quick question, actually?
Yeah.
So quick question just is, like you mentioned in the beginning about the shared representation. I just wonder if on a high level, you think, because in a way you could say, well, there is like an objective proof to like the physical state of the world or something. But is your point that you think that, because there are lots of different representations that are useful, like, I mean, obviously, just in terms of like bats using echolocation and some animals seeing in infrared and whatever, like, obviously, like our slice of reality is a somewhat subjective one.
Exactly.
I mean, in a way, like it's partial, let's say. It's not subjective necessarily, but it's like partial and also is a bit subjective. But I guess my point is, when you say shared representation, like, you could just replace that with like the objective truth of the world. But obviously we like, I mean, a lot of our perception is also filling in the gaps. Like, I mean, most of your peripheral view doesn't even include color. You kind of, there's even a blind spot in your eye that you can't get any information from. And we're very good at like in painting in our mind and so on. I guess my just high level question is like, to what extent do you think the human perception isn't ideal to strive for, like in a biologically inspired way, versus there just needs to be some objective, useful representation that might actually be quite different to humans? Like, I guess just where do you fall on that kind of debate a bit?
Yeah, so obviously, what you could do is try estimate every aspect of the real world, or basically try to quantify every physical property that you're seeing, at this single time point. But obviously that'll be completely overwhelming, completely intractable, and probably won't even be necessary for most tasks. So the key thing that I'm trying to like capture with this shared representation is that it's kind of not only estimating the true state of the world, but it's also capturing a representation that's kind of aligned to what humans
So like
expect,
with
or
semantic
what we
information,
use.
for example,
Exactly.
like with an object level of understanding and stuff like this.
Exactly.
Yeah.
Because the thing is,
It
like,
doesn't need to be exactly the same, but just like aligned to kind of human, which which also then brings into kind of, I guess, yeah, like object classification and like human level pre-training and stuff a little bit, I suppose.
Yeah. So that's exactly the point, because like this representation that we capture of the world, obviously it should be grounded in reality. So it should, if there's a object at a certain place, it should represent that object at that place. But then it doesn't, the actual information that it contains should more be useful to the task that we want to solve. So because we would be interested in certain types of information, the mobile device, the robot, should also have access to that information. Obviously, like defining exactly what that is tricky. So that's where the kind of learning and the task focus comes in.
Yeah, makes sense.
Yeah, but I would say on the spectrum of like a completely completely kind of task specific representation, or completely like objective world-based representation, I would say the optimal one is probably more in the middle, because you want to capture some factors. So the device or the robot should have access to some information that humans don't have, because that's how it will be able to do kind of tasks more efficiently, or answer more questions about the world. But then you also don't want it to like be completely task specific, so it just ignores everything else. So there's this balance between like an objective and useful kind of representation, or objective and completely compressed representation. But that's a very good kind of like discussion point, actually, because there isn't a clear answer for that. Great.
Well, we could talk for hours about that, so I guess I'll stop there and let you keep going. But thanks for that.
Yeah, sounds good. So for this first work, so this is the odometry, or the visual odometry. So basically, the problem here is that, say you have an autonomous vehicle, or you have a robot driving around the world, it needs to know how it's moving and also where it is. But in this case, we're just going to focus on like estimating the motion. And well, basically, to try to define this problem more rigorously, we'll say that we're given a sequence of images, so from a video or like a stream from a camera. And then what we want to do is we want to estimate the relative pose of the camera from the start of the sequence. And in this case, we're not given any other sensor information. So this is only the the RGB image coming from this camera. And then we want to estimate the position and the orientation of it. So you can see, like in this example, there's this is actually from Kitty, the Kitty data set. And then on the right, you can see this camera plotted and how it's kind of moving across this road. So, okay, so with the definition of this problem, you can, this is just kind of like an example here. So here we have two images. So on the right, we have image 1, image 2, and these are sequential. So they'll be like a single time step. So image 2 will be like a single time step ahead of image 1. And then what we want to do here is get the relative pose between those two images. So basically how this camera moved between the two frames. And I'm not sure how familiar everyone here is with kind of transformations and sort of geometric vision stuff. But basically, the pose of the camera, so the relative pose, is parameterized usually by a rotation and a translation. And the rotation would be described by a rotation matrix, so 3x3 matrix constrained to rotations. And then the translation would just be a 3x1 vector that describes the translation between the two center points of the camera. And then the minimal rotation, so you can convert these to a minimal rotation of 6 dimensions, or minimal transformation of 6 dimensions. And then this 6D vector kind of describes the translation between the two frames. So in this instance, what we're trying to do is take in these two images and then estimate this 6D vector for the two frames. And so in a traditional sense, I'll get you some like examples of failure cases and stuff later, but in a traditional sense, you would do this with a whole pipeline that involves feature extraction, feature matching across the images, and then doing a geometric estimation of the motion. But the thing is that this isn't really robust, so it tends to fail quite a lot. And then you also can't estimate the scale. So if you use, a completely geometric approach or completely traditional approach for this visual odometry, you can't estimate the scale, and like there's quite a lot of failures. So what we did in this case was, we took inspiration from some works that use a CNN, so just a convolutional network, to estimate the 6D motion vector directly. And in this setup, so this is basically the kind of like simplest setup of solving this with a learning-based approach. And here you basically take the two images, stack them along the channel dimensions, and then get this CNN to regress this 6D vector. And you train this with the ground truth poses that you can get from like a sort of a visual inertial setup, or from GPS, or some other sensor that you might have access to in the training environment. So using the CNN with the two images stacked as input gives some reasonable estimates. But the thing is that with this learning-based approach, the estimates that you get aren't as accurate as the traditional geometric-based ones. So while the CNN can learn to be more robust, it isn't more accurate than traditional estimators. And the reason, or one reason for this, is because it doesn't take into account the sequential nature of the video stream. So like I mentioned in the example before, if you're driving along the street, or walking in a museum or wherever, you don't immediately jump from one position to 100 meters away or something. You always have some like temporal stability, or like you have some smoothness in the motion. So what we kind of did with this DeepV0 work was basically use a recurrent element in the model. So we try to capture this temporal relation between the frames. So how this works is it uses the CNN as the base kind of prediction model, but then just applies the CNN to every two pairs in the sequence. So this is kind of like a sliding window where you take a pair of images, jump one step to jump one time step to the future, and then kind of just go along like this until you have reached the end of the whole sequence. And then these individual predictions are then tied together using a memory element. So basically how this works is you take the CNN, it predicts a feature vector that's propagated to the next time step, and then this memory vector, or this feature vector, is combined with the prediction, or the encoding of the two images from that time step, and then that produces the next prediction. So basically from the CNN, you have two outputs. You have your actual camera motion estimate. So that's the 6D vector that is predicting for the relative motion at that frame. And then you have this memory vector, which like shares the information across the time steps. And the result of this is that the predictions are a lot smoother and a lot more accurate, because if you can actually learn the dynamics of the platform, so the car or the person or the robot, then the CNN can, or the RNN network can actually learn what is an expected motion between frames, and then use that to make a better prediction of the motion across the time steps. So basically from this recurrent structure, we get more accurate estimates with less noise and better robustness than a traditional kind of geometric approach. So this is the exact result that then kind of shows this. So in this example, there's the green one is a traditional geometric SLAM approach, so ALP-SLAM. And the red one is our DeepV0 method. And then the blue one is the ground truth. So the ground truth here we obtain from like a visual inertial setup. So that's basically a synchronized IMU sensor with a kind of wide angle camera. Everything synchronized, global shutter and everything. So this gives a very accurate estimate of the pose. And as you can see here, so the ALP-SLAM, it quickly degrades, the estimates quickly degrade in accuracy and kind of drifts quite a lot. And then the learned DeepV0 one has a much better estimate. So it actually follows the ground truth all along the way. And then the thing you can also see here is that the scale, so the ALP-SLAM scale drifted so much that the overall length of the trajectory wasn't even close to the ground truth. Whereas the learned DeepV0 one follows actually has pretty much the same length as the ground truth in terms of the distance covered. So yeah, basically from this you can see the learned recurrent network is able to not only capture the scale quite accurately, but it also more accurately estimates the direction and the actual motion of the person walking through the museum.
Quick question on that. Were the images just channel-wise stacked before passing to the convolutional layer?
So yes, in this case they were stacked, but they were going through FlowNet. So it was going through an optical flow network first, and then going to the CNN.
FlowNet didn't have the first version of FlowNet didn't have the cost volume, I don't think. Because I was going to say cost volume would be really helpful for this. I guess now the state-of-the-art stuff, well, state-of-the-art probably is using transformers, but I guess there was a period where state-of-the-art was using things like cost volumes and stuff, maybe. Because I guess otherwise the receptive field of like the filters, there needs to be image alignment. Otherwise, if there's too much, just like if they've moved away too much and you do channel-wise stacking, then the features won't align and the filters won't even capture the correspondence, I guess. So I guess that's how FlowNet helps to avoid that problem.
Yeah, so that's why the kind of like flow.
Did you use? Sorry, did you use FlowNet to warp the second image, then get a warped image and the original image so that they're more aligned?
No. So in this one, we just took the two images, fed them through FlowNet. It was FlowNet 1 actually, and then feed that to the CNN. So it was just no alignment. Or
so there'd be no alignment. So that there'd be channel-wide stacked with no alignment. So if they were too far away and it was beyond the receptive field of the filter, then it just wouldn't work that well. But there would at least be the flow result in the same channel.
Yes, but the thing to consider there, though, is the receptive field across all the layers of the CNN is quite large.
Yeah.
So across one layer is small, but then as you go further and further. So yeah, but that is a good point, because if it can't
for the early layers,
exactly,
if you need to detect like low-level filters at the beginning that depend on both images, then you can't. But you can kind of detect features in the images independently or something, and then over time like correspond them. Yeah. Another quick question is the LSTM, because obviously, I mean, this is obviously very early work, but like the LSTM, the memory, was it just an LSTM at the end of a fully connected layer on the CNN? So I guess the actual memory that the LSTM holds has to be pretty simple, kind of global information that's not super spatially tied. So I guess like, what's the intuition about what that memory even contains? If it's like one vector that's like capturing really global information about the image, I guess it's interesting what that even represents in this case.
Yeah, so the thing is, this vector was actually just I think it was 1024 dimension, 1D vector. Like what I think it contains is just a sort of an estimate of the previous camera motion.
Yeah.
Maybe with some extra information about kind of like the state, so the velocity or something like that. But yeah,
I guess it's more motion based than vision based, I can assume, at that kind of size vector.
Yeah.
Okay. Yeah.
But now I mean, if you would kind of like to modernize, I mean, there are some, more recent approaches, building on this and stuff as well. But I think for the actual, flow estimation and things like that, you'd probably now use like Unimatch or some, state-of-the-art kind of cost volume stereo matching approach.
Is this, sorry, I know we can detract, but is the state of the art in optical flow? I know that Perceiver.io, for example, that as a transformer, they got state-of-the-art optical flow results. They beat PwC. Now, for example, do you know if the state-of-the-art optical flow results are now transformer-based?
I think so, but still with like CNN encoders, I think.
Okay.
So I think at the moment there's like Unimatch or GM Match, which is a transformer-based one, but I think they do have convolutions at the start to kind of like extract some features. But I could be wrong there. I'm not entirely sure.
Yeah, I'll do a bit of homework. It's fun to get back into my kind of computer vision roots a little bit.
One thing with that though is like what I've noticed is most of the approaches have actually gone towards like a multimodal thing. So basically estimating kind of disparity, flow, depth, all this stuff like at the same time, because it does seem to kind of benefit the training.
Makes sense.
Yeah, great. So so basically this work that I was talking about or just describing was the base one. So this was DeepV0 that we did in kind of 2016 or 2017, and then we also have a similar network, but similar method, but integrating inertial information too. So with this VINet, the only difference kind of is that with the DeepV0, we have a single memory vector that feeds to the next time step. But with the VINet, we have another stream that processes the IMU data to a feature vector, which is then concatenated with the visual feature, and then fed through the network to produce the motion estimate. And then there's also work that we did on localization. So with this approach that I was just describing, we're estimating the relative motion between frames. But in many cases, you're also interested in the absolute location. So kind of like saying, where are you in the world? And this is kind of like what GPS would do in an outdoor scenario. But with this vidlock, what we did was extend this type of DeepV0 approach, but to absolute poses. So you can give it a few frames, and then it'll tell you, okay, you're next to the museum, or you exactly at this location. And then the last one I mentioned here is just extending the DeepV0 and the VINet approach to a probabilistic one. So if we can get probabilistic estimates of the motion, we actually have a sense of like uncertainty, and we can fuse this information with other sensors and models. Yeah, great. So with this, we would with the DeepV0, VINet, and ones like that, we were talking only about the motion or the location of the device. But something that we also quite interested in, obviously, is like what is around the robot, what is around the device. So you can basically, instead of only estimating the motion of the device, you can estimate the geometry of the scene in a joint manner, because these two kind of properties of these two variables actually tie together quite nicely in something that's known as structure for motion. So yeah, basically just to give a very intuitive, high-level overview of how this basically localization and mapping works is through a process called bundle adjustment. So in the case that we just saw, we have like, a series of cameras. So it could be from a video sequence, or it could be just from like images taken of a scene. And then if you pick a point, so a single point in the scene, that point will be visible in multiple cameras. So it could be, as you're moving across the scene, or kind of moving forward, for example, the same point will be visible in multiple of the frames. So then if we make an estimate of where that point is, and we know the camera position, as we were just talking about in the previous example, then you can actually project that point into these cameras and get an expected position. So that expected position obviously doesn't match exactly where the true location of the thing is, or the true location, the true pixel location, but it'll be kind of close if you have a good initial estimate. And then what you can do is you can basically define a cost function that measures the discrepancy between the projected location of that pixel and where you detected the object, and then iteratively refine the position of the cameras so that the detected location actually coincides with the projected one. And this iterative process is what is known as bundle adjustment. So how this adjustment is actually done is through a process called structure for motion. So how we do it is we form this residual. So that's the error values. So that's kind of like, in a deep learning sense, you would have your loss function or your error function. And then you would compute the Jacobian. So that's the derivative of the residual function with respect to your variables. So in this case, the variables are the positions of the cameras, as well as the 3D points in the scene, because we want to jointly estimate where the cameras are and where the 3D points in the scene are. And then the update step that you usually apply in bundle adjustment is a little bit more complex than normal kind of SGD-based optimization. And it basically just uses the Jacobian and the residuals to compute this update step that takes into account the structure of the error surface. So the kind of key difference between this and sort of like an optimization that you would do with a neural network is that this can converge faster, because it basically knows how big of a step to take. So if the loss function is very flat, it'll take a big step. And if the loss function is very sharp, it'll take a small step, so that it actually doesn't jump across and miss the minima. So this is a very, very good optimization to use for this structure for motion process. But the only problem is, and this is also why this isn't really used in deep learning, is that this Jacobian matrix, so this residual with respect to the variables, becomes very large when you have so many, or if you have a very high dimensional space to optimize over. So in the case of solving for the camera poses and all the 3D points in the scene, we actually have a h by w, so it's height by width matrix, which is incredibly large, and then you still have to invert that to compute the update step. So basically in this work, CodeSLAM that we did, we tried to solve this issue with the intractable update, or the intractable Liebenberg-Marquardt step. And the way we did this is basically using autoencoders. So just as the problem setup, we again have two images. We want to estimate the motion, but now we have an additional thing we want to estimate, and that's the depth of each pixel, so the 3D location of each pixel. And as I mentioned with the bundle adjustment, if you have the motion of the two frames and you have the depth image or the 3D points, you can actually project those 3D points into the second image. So you can take the pixels in the first image, use the depth and the motion, and then project those points to see what the second image should look like. And if your motion and your depth are exactly correct, then your residual should be 0. It should exactly align. But if it isn't, because you don't have a perfect estimate of the motion and the depth, then your residual will be non-zero, because it's going to project this first image to some random location, and then your residuals will be high. And then, yeah, based on these residuals, you can compute the update step, like I mentioned before, this delta, apply it to the motion and the depth estimates, and then try to get a better and better residual estimate until you find the minimum. However, like you saw, this update step is incredibly high dimensional, or the Jacobian is incredibly high dimensional, so it's not really tractable to compute this update step. So what we did in this work is basically use a decoder, so trained with an autoencoder, but this goes from a low-dimensional code to the depth map. So in this sense, we actually parameterizing the depth map, not by this very high-dimensional depth value for every pixel in the image, but we're parameterizing it with this low-dimensional code that we can convert to the high-dimensional depth image using the decoder. And then instead of optimizing this high-dimensional depth image, we just optimize the low-dimensional code. So yeah, this is kind of like an example of how you can use representation learning, or better representation of the scene, to make these excellent algorithms tractable or more robust in a real-world scenario. So yeah, basically this CodeSLAM approach uses a decoder, or uses a code to represent the geometry of the scene, which is translated to the depth image with the decoder, and then we optimize this code and the motion, so the pose, to get the minimal residual between the sequential frames. And this is what we get. So this is showing a camera just moving through the scene, and you can see that the position of the camera, as well as the geometry of the scene, is being estimated quite quickly and robustly. So this shows so basically each keyframe that we take, we just project that depth into the 3D scene, and then we join them together to get this like larger map. But the key thing here just to see is like the motion of the camera, as well as the geometry of the scene, is being estimated in a joint manner. And it's a dense estimate, so every part of the surface is estimated, not just like key points and sort of lines or something like that.
Was it all pixel space residuals? I don't know if there was ever any kind of feature space residuals or anything. It was just pixel space?
Just pixel space, so just like that. Just the difference between the images.
Yeah, it'd be interesting. I guess like feature space would make it a tiny bit more robust, but I guess it was just kind of, that wasn't what the paper was about. It was more about this kind of low-dimensional code, basically, I suppose.
Yeah. The thing is, this still had lots of like failure cases, and because basically if there's any change in the lighting between the images, then the residuals don't get meaningful, and then it fails, and reflections and all sorts of other things as well. So basically, like that's actually a good point. So that's where this next work comes in. So there were two problems with this CodeSLAM approach, and the one is the convergence can be slow in cases where it doesn't have a well-conditioned residual function to minimize. And the other thing is it often fails in degenerate cases. So that's kind of like if you have reflections or sort of specularities and things like that, it doesn't have a way to actually model it. So the optimization doesn't give you a good solution. So with this least squares net, what we tried to do was, well, basically bring in learning into the process again. So instead of using this analytical update, this Liebenberg-Marquardt update, what we did was use a LSTM cell to predict this update. And then this update, or this LSTM, is trained on ground truth, depth data, or ground truth depth and motion data to actually produce robust estimates of the updates. And as input, this LSTM cell gets the Jacobian information and the residual information. So essentially, it should have the same ability as CodeSLAM to do the updates with the traditional LM step, but then it should be able to kind of learn some priors or be more robust in these kind of like adversarial conditions as well. So yeah, the setup here is basically the same. So we have the initial estimate of the motion, initial estimate of the depth, and what we want to do is get this like the target depth by doing a few update steps. And then in this case, we have this learnable or learned optimization unit in the center instead of an analytical update. And the way that is structured is we compute the residual, we compute the Jacobian, feed it to this RNN. RNN predicts the update step for the variables, so for the motion and the depth. And then we update the variables, get the new estimate, and then iterate through this. So we estimate, compute the residual again, and then iterate through this for a few steps so that we get the refined estimate of the depth and the motion. And
what was the architecture of the RNN? Sorry, quickly. What was the architecture of the RNN on a high level?
It was just it was LSTM, and it was so this Jacobian we fed in as like, it was a 2D. Was it a 2D or was it? No, it was a flattened vector, I think. So the residuals and this Jacobian were flattened into a multi-channel vector, and then those were processed through the RNN.
So, but was all like, but was there no CNN component? Because the residuals kind of form an image in a way.
Yeah, no, I guess. Yeah, I think that is true. I think we stacked the residual image with the Jacobian that was reshaped into a H by W image, so like a 2D multi-channel thing, and then that was it was a convolutional LSTM. So the hidden space was like a 2D cell.
Not too dissimilar to like DeepV0 or something. I mean, not entirely different. It's kind of a CNN with an LSTM on the end, basically.
Exactly. Yeah. Yep.
Yeah. So I'm making you think back a long while.
It's been some time for this, but yeah. I think that is right. Yeah. So basically, this example is just like a toy example. So comparing this learned LCM optimizer to Adam, and as you can see here, and this is just like a simple curve fitting example with a sine wave. So the two things to notice here is like the convergence is much faster for the learned optimizer, but then it also, I guess you can't really see it here, but like a standard optimizer, if you don't have the learning rate correct, or if you have some some noise in the data, then lots of times it doesn't converge. Whereas the learned optimizer actually usually converges to something that looks like the stuff in your training data. So it has this prior about like what the output should look like. And then this is an example of the depth and motion case. So the estimating the motion and the geometry at the same time. And this is just showing the iterations in the optimization as well. So you can see how it kind of like refines the depth as it gets more and more frames. Yeah. So yeah, I think that was all I had for today. So basically just like the conclusions from this kind of line of work, I think is, so digital twins or this like, virtual representation of the world is essential for most AI applications, whether it's in robotics or autonomous driving or AR, VR. And the base kind of like factors or the properties that we want to estimate are motion, shape, light, reflectance, and semantics. But in this talk, I've kind of focused on the motion and shape part mostly. And yeah, this is kind of like an open sort of research area still. So if you can, get a good way to estimate the motion and depth and these factors, it can have a really big impact in kind of many areas like robotics, augmented reality, and natural sciences. Yeah, and these are just, this work is not just done by me, it's like with all my collaborators and students as well. So yeah, thanks a lot.
Well, first of all, thank you so much, Ronnie. Really, really interesting, and also really good for me to go back to some nostalgia for some of obviously the work going on in the lab and stuff I've been very familiar with. Nice blast to the past. Yeah, well, already it seems like we've got some questions. I think there's probably some on YouTube, but certainly some as well on the call. So maybe Guillermo, do you want to go first with the question?
Yeah, sure. So this is really probably a high level or maybe open question, but I guess most of this research applies to monocular image instead of binocular image. And I mean, I see the point, and disclaimer, I really find monocular image very interesting, but do you know there is a point to study monocular image instead of just getting another camera to get the depth like information?
Yeah, so I mean, that's a very good question. So the work that I presented here mainly focused on monocular cameras. But the thing is, the concepts also apply to stereo or multi-view setups. So the question, yeah, like stereo versus or LiDAR versus a monocular camera is also like a very, it's a good kind of like discussion and debate question, I would say. Because the problem is, so in a recent setup that we were trying to do, so volumetric capture for like clouds, for atmospheric science application, we did use stereo cameras, but we had to have like kind of a large baseline. And the thing is just calibrating that stereo setup and making sure it doesn't change over time, and basically kind of like just ensuring that you can actually use or benefit from the stereo itself is also a tricky process. So it's kind of, it's a bit of a trade-off, whether you can have a very controlled, stereo setup, or whether you would, maybe want to be more robust or like have a more complex algorithm but go with the monocular case. There's a lot of like trade-offs that you need to consider, I would say.
Yeah, I see the point, but don't you think that there is, even if you don't have like a properly calibrated system, that there is some room for improvement? Like, for example, in the visual odometry paper, the first one you have presented, my guess would be that even if you don't calibrate the system, but you fit the binocular images to the system, it would work better because it simply can infer some kind of depth information.
Yeah, definitely. So the thing is, I guess, obviously adding more sensors can get you the best estimate. That is kind of like not, it's kind of an undoubted sort of thing. But the thing is that you need to, for example, say you have a stereo setup, and your one camera rotates a little bit. Now, if you use rectification and standard kind of like pipeline where you're just doing matching across the epipolar lines and stuff like that, that's all going to get screwed up if it just changes by this little fraction, like a fraction of a degree. So yeah, so obviously you could then train a model that is robust, or like you basically in the training data, you do these little offsets or these displacements to simulate the calibration error. But then it's kind of like then you have sort of a, basically you have a hardware that's more complex, and you have like the algorithm or the software that's more complex. So I mean, I would definitely say, more sensors, more cameras would definitely get you a better estimate. So if you need accuracy, definitely go with more cameras and more sensors. But there are difficulties that come with that as well. So it's not like it's not like a clear case where you can just say always use stereo.
I guess sometimes as well, these research questions are kind of, even if they're not really reflective of like the reality of real world systems, they're kind of, I don't know, kind of deliberately more hard than it would need to be necessarily, but that kind of gives the test bed for like algorithmic insights to happen that then do generalize to real setup, where there is of course more data and more sensors and everything. So I guess sometimes there are problems that are a bit like deliberately constrained to be harder than they might be, but that kind of sets the scene for then interesting algorithms that probably then generalize outside the bounds of the problem statement as well, I suppose, and things like this. I've always been one to think that, obviously some of the hardest things, well, just in general, some of the hard things are kind of, even if you have depth and everything and all of that solved, even then knowing how a robot can interact with it and do things is still a big challenge. So there's all kinds of different kind of missing pieces, and even like ground truth kind of depth and everything in a simulator still doesn't mean you can have a robot that can navigate that space and use it and everything. So they're all kind of different problems that need to be addressed for a holistic kind of AI to interact with the world and everything. But
just another point with that, just kind of like in the case with the stereo, which people usually mention as well, is something you have to consider. There's the limited range corresponding to a certain baseline. So if you have a stereo baseline of like, say, 10 centimeters, you're going to have a usable stereo range of like probably 1 meter to like 5 meters, depending on what your resolution and stuff is. So it's
we also do pretty well on, I mean, even though this is probably more like monocular depth estimation, but we also do pretty well like playing video games, which are like monocular or stuff. Like obviously we can like deal with a lack of stereo pair, or we can like watch a movie without like wearing 3D glasses and like kind of get what's going on, like in terms of like the 3D reconstruction of the scene. So obviously like we can do a lot with monocular, that probably has more to do with like semantic depth than it does to do with obviously structured motion. But so Arsh has a question as well.
Yeah, just a follow-up question on sensors actually. So my question is, where do you think research on LiDAR-based imagery is going? Because we see all of these new startups on autonomous vehicles, right? So Wave and then AI and Tesla, they say that a camera is just enough to do the job, and we don't really need those the huge LiDARs that companies like Waymo are using. So
it's a very good question. I think it's a similar case, I would say, with the stereo versus monocular, because I mean, with LiDARs, obviously you also have a lot of disadvantages. So you can't just slap a LiDAR on the car, incur some extra cost, and then your kind of spatial awareness and world model is solved, because the LiDAR has limited resolution scan and kind of lots of other. If it's a very dark object or reflective and things like that, it also doesn't give a reliable estimate. So it definitely helps, but I would say for a scenario like autonomous driving, multiple cameras is probably the way to do it. So a multi-camera setup. We have like multiple overlapping cameras looking at the scene. If you can have like a LiDAR or something, that obviously helps, but I would say the ideal is kind of a multi-camera setup.
To follow on that, would you say, do you think, like, I don't know what most are doing now, to be honest, but do you think most multi-camera setups would then just like, let's say, feed that in as raw data to a neural network? Or do you think actually then having some calibrated stereo baseline so that like before there's any learning involved, you have a point cloud that is extracted from like conventional mechanisms, or even with networks that given the baselines that are calibrated or something, I guess maybe, I guess there's a spectrum. You can just feed it all into the raw data with the poses and let some kind of planning algorithm work everything out, or you can like give it this like structured representation. I don't know, what do you think there?
You definitely need structure. So I would say like probably not feeding it all into like this, single network, just trying to discover everything itself. But probably some registration, like kind of processing maybe the overlapping views with one model, using some of the geometry there, but not assuming like a completely accurate kind of calibration, for example.
That makes sense. I know we're going over a bit, but any other questions? Yeah, James.
Yeah, we have 2 questions from YouTube. So the first question, I don't know if this was covered or not, but Sumya Dip asks, any ideas on how to estimate the depth in an unsupervised manner?
So I guess there has been quite a bit of work on doing unsupervised depth and motion. So you basically form a loss function based on this reprojection error. So you have a network predicting the depth, you have a net predicting the motion poses, and then you reproject the one frame in the video to the other, and then you compute the loss based on that, and then you can train the networks over kind of lots of sequences. There's also been work on kind of using stereo setups where you form a loss based on the stereo error, and then kind of, just with like single frame or pairs of frames, you can also train a depth estimator. It works quite well, but like obviously if you have ground truth or like depth data that's really accurate from some other source, then you can train better models, really.
Okay, thanks. And then David Gelberg asks, where do you see the biggest challenges or bottlenecks in real-time 3D vision over the next 5 years?
So I guess good quality data is one. So for most 3D tasks, if you want to go in a kind of like more complex, so if you actually want to start learning 3D priors about the world, or like directly estimating, 3D geometry and spaces, then you need high quality training data to actually sort of train it on. So in most of these cases, we were representing the geometry with like a depth map, or like sort of more simple, a representation that you can handle more easily with networks. So just a 2D thing. But if you're going more towards full 3D, then you need high quality data. You need also lots of memory and things like that. So I would still say 3D data, high quality data is probably still the challenge.
Awesome, thanks.
Well, I obviously we don't want to keep running for too long, but there's a couple more. So Ash, I also have one more. But Ash, you got a question?
Yeah, just a quick follow-up question on that. So where do you think this is heading in terms of deployment? Because when we talk about these 3D models, I'm pretty sure they're very huge, right? So they're not scalable to mobile phones and edge devices and all. So efficient is my question. Sorry.
So I would say that the models themselves are scalable. The challenges come in when, for example, so bandwidth is one challenge actually with these multi-camera setups, because if you have a system that has like 6 cameras attached to it, you have like 6 HD feeds that are coming in live, and then you still want to process all those with a network. So even if your network can kind of process, one frame at like 20 frames per second, if you have these 6 kind of feeds coming in and you want to process them all at something like 30 frames per second, it becomes a bit like difficult. But obviously the hardware is kind of improving, so I think that kind of issue will be addressed just with like improvements in hardware. In terms of like the inference and stuff, quantization, sort of all these efficiency tricks, they definitely do help in deployment, because the real difficulty is kind of like if you're working with some basically with a situation where you need to do high frame rate decisions or high frame rate like inference, where you can't like miss, or have like a thing running at 5 frames per second, and then you've kind of missed the turn, or you're trying to catch an object or something like that, and then you just can't do that with like lower frame rates. So there's a huge challenge there as well. But I would say that to some extent that is more hardware. So the hardware does have to like develop further to actually to get there. But obviously the software optimizations can help a lot as well.
Yeah. So I mean, in a way of summarizing is that majority of these challenges are outside the realms of deep learning and more related to bandwidth, networking, and hardware. If I got that right.
Yeah. So I mean, the kind of like specific example I was just thinking of is kind of like, say you're trying to estimate the path of, like, say you have a drone flying through some space, and then you're trying to like estimate or do collision avoidance, or kind of make some decisions based on, I don't know if it maybe has to avoid sort of like a flying ball or something like that. In that case, you can't be going and doing that with like a network predicting from the raw images where the ball is and kind of trying to triangulate and stuff, because the network will only run at kind of 10 frames per second, and you probably need the information coming in at like at least 120 hertz or something to make the decisions that fast. So I think it's kind of like it's more of a design problem where you have to decide what basically where you actually want to use the full sort of power of a network to predict or make the decisions, versus where you can actually sort of trim it down or make it much more efficient using some other sort of way. So in the obstacle avoidance case, obviously you can have some other sensor that takes readings much faster and just does a kind of like very simple obstacle avoidance planning or path planning. But yeah, so it's basically, I think it's just a case of kind of like designing the solution with the constraints in mind. So knowing what you can accomplish with the models, how fast you can do the inference and stuff.
Yep. Thanks.
I know. Then we'll probably have to wrap up. But also, Joshua had one as well quickly, which we do at the end. But my final question is just like, obviously what we've seen in LLMs is that you can basically do this incredibly simplistic autoregressive pre-training of large language models based on like all internet data ever created. And it's an area of research I've not followed as much as I would have liked in the last year or so. But I'm very interested in the like computer vision analogy, let's say, and there's things like DynoV0 and things like this. I guess my question is, in a year's time or at some point, do you think all depth networks, all like, I don't know, kind of monocular networks or visual odometry networks, are they all going to be pre-trained from big foundation models such as DynoV0? Are the features that are learned by DynoV0 transferable? Do you think foundation models and computer vision is something that's going to kind of become a big part of the research?
Yeah, so that's a very good question as well. Actually, for discussion really. But so what I think is these kind of foundation models, there hasn't really been a true computer vision analog of large language models yet. And the reason I think that is because with the large language models, you can actually change the task they're doing without retraining part of it or fine-tuning it, for example. Just with the prompts. But with most of the computer vision models, you have to still do fine-tuning. So with Dyno, for example, you have good features, but you still have to adapt it to the task you want to do.
So there's no works that try to kind of, well, I guess you still need to do it, but I mean, is then like, did you have to do fine-tuning through DynoV0 itself, or has anyone tried to like slap on a few extra layers and only update those, and maybe the features themselves kind of latently contain the information? Well, I guess they do, but it's still a form of fine-tuning, I suppose. But
exactly. So I mean, there's definitely like sort of having an adapt on top of the but the thing is, you still have to train that on the task you're doing.
Yeah.
What I'm kind of talking about is like saying you just give it an image, give it an RGB image, and then say, can you estimate the depth of the, this point, this pixel, or convert this to a depth image, or convert this to a normal image, or,
Yeah.
Yeah.
It's a shame not all labeled data, all the millions, tens of hundreds of millions of images come with depth data and everything as part of them, I guess. I guess it's not obvious. Do you think that paradigm shift something that may happen, or do you not see how that would happen?
I think it'll happen sometime. I mean, at the moment, there isn't kind of the data or the training setup yet that can accomplish that. But it's definitely something I think that will happen soon.
Yeah, sounds good. Well, I guess because Josh just says as well, but I mean, I can maybe answer this a bit. But so Joshua just said that he's really interested in all of this, which is first of all amazing. So am I. But what research opportunities and funding is available? I mean, I just broadly, obviously, it's an area that lots of companies and governments invest research in. Only more and more with AI becoming bigger. But I don't know if you want to add a point to that at all, Ronnie.
Yeah. So there's tons of obviously like startups and kind of companies hiring in this direction. In terms of research opportunities, there are scholarships and things like that at most universities. I wouldn't say there's kind of direct funding or sort of positions open specifically for these topics, because kind of like the research is usually advertised in a more general sense, but like there's tons of like general opportunities that you can apply for and are open around the year, I think.
No, absolutely. And I sort of maybe just say on that, because I'll be trying to be respectful of everyone's time, but also after just saying about are there tricks like flash attention for geometry processing, and could this be a research prospect itself? One thing I'll quickly say to that is that transformers are massively used for vision anyway, so flash attention itself directly is very relevant to a lot of computer vision stuff anyway. I guess I don't know if you have any quick.
I meant if the data points are maybe meshes and like point clouds and something, because processing that it's latency intensive, right? So
yeah. Well, yeah. Do you have any points on that, Ronnie?
Yeah, definitely. Like I think I don't know. I'm not exactly sure about the details of like flash attention, but like any sort of adaptive processing or any kind of because with point clouds and these kinds of representations, the trouble is always they don't have much structure. So you can easily reduce the number of points, just kind of randomly sample things like that to make the inference more efficient. So yeah, anything that can kind of do adaptive processing can kind of like work without needing a regular grid of pixels or voxels.
This is actually very relevant to things like neural magic as well. Actually, there's a lot of work that shows that particularly for incredibly sparse graphs, and obviously things like graph neural networks are very amenable to this kind of sparse representation. When there's not a huge dense grid structure, you can do very good things with just running like depth-wise or like depth-first execution of graphs on CPUs and stuff. There's a lot of really interesting stuff there that I think is very relevant to this kind of stuff as well. But I guess in a way, like the big core engine of things is increasingly becoming transformer based, and therefore I think anything like flash attention actually transcends computer vision anyway, to be honest. Cool. Okay, well, I know I'm sure we could ask a million questions and we could discuss all these things at length, but I guess we should wrap up for today. But again, I want to say thank you very much, Ronnie, for going through all of that. That was super interesting. Let's all give a metaphorical and kind of hand clap for Ronnie there as well. I just raised my hand. I got it wrong. I don't know what we're doing next week. I think next week Guillermo will be going through a paper, but I've forgotten the name. So stay tuned for what that is next week. What is it you're going through next week, Guillermo?
Yeah, it's actually the segment anything from.
Okay, amazing. Well, we'll be going through that next week. So yeah, I'll see you guys all again next week. Hopefully we'll have you again at one session at some point, Ronnie.
I might join next week as well. Sounds interesting.
Sounds good. Yeah, we'd love to have you here. Sounds good. Cool. Okay, well, have a great evening, everybody. Thanks a lot for joining on YouTube as well. See you guys all again soon. Bye-bye.
Thank you.